Hello, it's Stat 135, Lecture 38. Last time we were doing section 14.5, multiple linear regression. So let's review. We have a linear model. Y is x beta plus e. Beta are our k. We have k predictors and beta 0. We have E as our errors. These EIs are IID, normal, 0, sigma squared, homoscedastic. X is our design matrix, which is full rank. And we can test which predictors Xi are related to Y. So our null is that these beta I are all 0. The alternative is that at least one of them is not 0. We have an F statistic, degrees of freedom k and n minus k minus 1, that can be written in terms of the coefficient of determination, r squared over k over 1 minus r squared over n minus k minus 1, where r squared is the model sum of squares over the total sum of squares. It's a number between 0 and 1. We can test individual beta k to be 0 using a t statistic, t with n minus k minus 1 degrees of freedom. The standard error for each beta I hat is given by this formula here. And we see in the denominator we have 1 minus ri squared, where ri squared is the r squared obtained by regressing the xi on all the other predictors. So if the xi are correlated, in other words, we have multicollinearity, then the ri will be close to 1 and the standard error squared for beta I will be large, which will cause a large variation in the coefficient beta I hat. It'll be difficult to reject that beta I is 0. We'll get a small t value. If we add a correlated predictor to the model, you wouldn't expect r squared to go up much because you're not adding much of anything new to the model, but it will go up a bit because as we saw last time, r squared goes up every time you add another predictor. So for that reason, we look at r squared adjusted, which is defined so that it won't go up. Just because you're adding a predictor, it'll only go up if you're actually increasing the ratio of MSS to RS to TSS. How to choose predictors for your model and what to do if you have multicollinearity is beyond the scope of this class. Go take Stat 151A. Today we're going to look at some multiple regression examples. Next time we'll start Bayesian statistics. So here's an example on B courses that has two predictors, a patient's height and weight, and the response is the response variable is the length of the catheter, and we're trying to predict the length from our predictors. So the assumptions we have in our model is that our data xij, these are fixed numbers in the design matrix, is full rank. That the errors are IID, normal, 0, sigma squared. That the errors are homoscedastic. Okay, so using the catheter length, we make a scatter plot, and we calculate the correlation between height and weight. Scatter plot with length and each of the predictors. Then we can look at the correlations, and we see a high correlation between height and weight, 0.96. So so now we're going to make a linear model, a simple linear regression of length on height, and we see from this that we can reject the null, so there's a significant relationship between them, and we can look at the residuals, and that's not great, but I would probably see if I could transform my I would possibly transform one of my variables so that I didn't have these tails that weren't following the normal, but then that would compromise the interpretability of the model, so not sure. And we can similarly do it for length on weight, and it also says that we can reject the null. This has a better fit of the residuals. Then we look at multiple linear regression, and because of the correlation we have multicollinearity, and indeed the F statistic says to reject, but the T statistic says don't reject. So again, this is because the standard errors are so large. So again, looking at the residuals, and that looks fine. So this hopefully will help you with your homework. We then did a in-class exercise that required some calculating here. So we have two objects located on a line at points beta 1 and beta 2, and these points aren't precisely known, and so we make measurements. So our measurements are y1, y2, and y3. y1, we're measuring beta 1, the first object, the distance to the first object. y2, we're measuring the object to the second object, and y3, we're measuring the distance between the two objects. And we set up a linear model here. Here, by the way that it's defined, the x's are 1s and 0s and minus 1s, as you can see. And so I've written out the matrices that I have, and we want to find the least square estimate of beta 1 and beta 2 hat. So these are estimates of these lengths. So this is a good example of some linear algebra here. If we look at the solutions here, you would be calculating x transpose x inverse and showing that that's 1/3 times this matrix 2, 1, 1, 2. And then x transpose y is 9, 11. So beta hat then is 1/3 times 29 and 31. And we can then find our estimate sigma squared. Sigma squared is RSS over n minus 2. We have two coefficients we're determining, hence minus 2. And the RSS is y minus y hat transpose y minus y hat. And you can go and compute this directly, and you'll get sigma hat squared is 1/3. And then we can compute the standard errors. So we can compute the the variance covariance matrix and pick out the diagonals, and that is the variances. So we would then take the square root of 2 over 9. Finally, we want to estimate beta 1 minus beta 2 in its standard error. So an unbiased estimator would just be beta 1 hat minus beta 2 hat. So that's minus 2/3. And then the variance of beta 1 hat minus beta 2 hat. So we'll have to read off the variance and covariance terms of our variance covariance matrix. And then we see that the variance is 2 over 9. And so the standard error is the square root of that. And finally, we want to test the hypothesis that beta 1 is equal to beta 2. So this is straightforward. It's a t-test here with n minus 2 degrees of freedom, or 1 degree of freedom. And we got a test statistic of minus square root of 2, which if you put in R, you'll find that that has a p-value of 0.2. So we do not reject the null. Okay, so I hope that was helpful. We will start Bayesian statistics next time. Have a good day.